All right, so we've come to the final lecture for linear algebra, which, really is just the beginning of what linear algebra is, as it turns out. But for us, it is kind of a natural stopping point, in essence. We've spoken in chapter 7 about abstract vector spaces and subspaces, and we know about spanning and linear independence from 7.2. And so the last thing that we want to talk about uh, as kind of a cap to what can generalize from Rn to this more abstract setting is the notion of a basis and dimension. And I did speak of it last time. I kind of hinted at certain sets being possible bases for spaces without actually defining it. But let's actually go through and define it the same way we did in Rn, and then do a few examples to kind of show what can happen. All right, so the first question, the first thing is a basis for a vector space is the same as it would be in Rn. It's a minimal spanning set. And by that I mean it's the set has to span the whole space, which we know what that means from the previous section. And the vectors in the set have to be linearly independent. That's what we mean by minimal, right? So there can't be any extra vectors in there that can be written as linear combinations of the other guys, right? They have to be linearly independent. And so let's look at an example. We have a set of 3 functions, quadratic functions, and we want to know if it's a basis for P2, which is the set of all quadratic polynomials. And so again, by that what we mean is if it's a basis, we have to test for linear independence, and we have to see if there's anybody in P2 that cannot be expressed as a linear combination of those guys. All right, and so our first question is, if I multiply the first one by C2, the second one by C3, 2 rather, first C1, C2, and then the last one by C3, I want to set that equal to ax squared plus bx plus c, right? And I want to know for what a, b, and c can I find c1, c2, and c3 for which that's true. Okay, and so again, you're going to combine like terms. So distribute the c1, c2, and c3, gather the x squared terms, the x terms, and the constant terms. And that's equal to ax squared plus bx plus c. All right, and so we generate, remember, the only way these polynomials are going to be the same is if corresponding coefficients of their terms are the same. And so that generates a system of the form c1 plus c2 equal to a, 5c1 plus 2c3 is equal to b, and minus 2c1 plus 3c2 minus c3 equals c. And so what we're really asking is for what a, b, and c does this system have a solution, right? And so in matrix form, let's write this as 1, 1, 0, 5, 0, 2, minus 2, 3, minus 1. And remember here, technically we want to put bar A, B, C, but we're asking if it's a basis for P2, which means it would have to span P2, right? So all I really have to do is put this into echelon form and see if there's a 0 row. If there is no 0 row, then that means that this system would always have a solution, and hence these functions would span P2. All right. So if I do that, I'm going to multiply like we normally would. I'm going to multiply R1 by -5, add it to row 2 and put that into row 2. And then I'm going to multiply R1 by 2, add it to row 3, and put that into row 3. All right. And what that does is it gives me the following. The first row stays the same. Second one is that guy. And then the third one is that. All right. And then finally, I'm going to add row 2 and row 3 and put that into row 3 to get a 0 there. And in so doing, what I get is that. All right, notice that there are no 0 rows. And so let's call this set S. S, the span of S is P2, right? All right, good. So that's exactly the same as it was before. Furthermore, we want to know if they're linearly independent. Well, all you have to do for linear independence is put the zero vector on this side and see what the coefficients C1, C2, and C3 would have to be, right? So if we use this guy, so we're looking then at, so this is for linear independence. C1, C2, C3. And the zero function in P2 is 0x squared plus 0x plus c, which means that the coefficients are all zeros. All right, so we're solving a homogeneous system here. And notice this is going to work just by back substitution. C3 has to be 0. Then going back up to the next equation, minus 5c2 plus c3 has to be 0, but c3 is already 0, right? And so that's 0, hence c2 is 0. And then since c1 plus c2 has to be 0 from the first equation, and c2 is 0, we conclude c1 is 0. And so the only way to generate the zero function is by having all three constants equal to 0. And so yes, they're linearly independent. And so hence, we have the both conditions are satisfied, linear independence and the set spans P2. And so yes, S is a basis for P2. All right. And so remember, you can have infinitely many different bases for a vector space. The one that I said was the most natural is this one. It's like the ijk of P2 in essence, right? If you just use those guys, that's a basis. But so is this one here, where we're using different functions. Doesn't matter, right? As long as those conditions are satisfied, it's a basis. All right, let's moving on. So the next part, again, if we were doing this, if we had more time, if like in linear algebra, if we had like a whole year to devote to this, and you're probably saying, just kill me now. But if we did, we would actually go through and argue these a little more carefully. As it stands, we're just kind of making an inference that it worked in Rn and we're defining things the same way, so they're going to work. And so there's a little bit of trust built into this. But these are facts that are proven in the text. You can take a look if you want in your free time. But every vector space has a basis. So you can always generate a vector space with a bare bones set of vectors by forming linear combinations. And then everybody in a vector space can be written uniquely in terms of basic elements. So give me a basis for a vector space, give me anybody in the vector space, I can find a unique combination of those vectors that produce that element. So you can't express it in more than one way. That's important. And then the number, since we have infinitely many bases possible for a vector space, then what is true is the number of vectors in every basis has to be the same. And so that was true in Rn, if you remember. We had several different ways of generating Rn with a basis, but always those sets had n elements in them, right? Even though they look very different potentially, they still have the same number of elements in them. All right, and then here, this is kind of important for our purposes, actually both 4 and 5. So if you have a subspace of a vector space, its dimension cannot exceed that of the space in which it belongs. And that makes sense. It's kind of like a cardinality issue, but with respect to dimension. In the sense that if you have finite sets, if one is a subset of another, then the one that's a subset can't have any more elements than the set in which it belongs, because it's inside of it, right? Same thing here with dimension, is that if you have a big vector space and then inside you have a subspace, so it has structure of a subspace, the dimension of that subspace cannot exceed the dimension of V, right? Because after all, it contains a subset of the vectors that are in V. All right, so that's important. And then if you have a vector space with dimension n, right, so I know that its dimension is n, then any set that contains fewer vectors than n cannot span B. If it contains more vectors than the dimension, then those vectors have to be linearly dependent. And the only way, if you take a set of vectors and there are n of them in there, and that's the dimension, the only way it'll span is if they're linearly independent, right? So just knowing that you have n vectors in a set does not guarantee that it spans the whole space, right? You have to have linear independence for it to happen. Okay, so let's actually use some of these as well as some of the previous examples we talked about to find dimensions of these spaces. All right, so for Pn, remember Pn is the set of all polynomials of degree n, and so you need a basis to be able to talk about dimension, right? So a typical basis here would be 1x, x squared, and then up to x to the n, right? That's kind of the canonical basis for Pn. And so the number of elements in that basis is n plus 1, and so that's the dimension of Pn, right? It's the number of elements in a basis. And so you'd actually have to go through and prove that this was a basis in much the same way that we did in the previous example. But again, it takes more doing if you want to do it in general, right? You'd probably do this inductively. But again, we're not focusing on proofs here. But that was what you would have to do if you want to prove that statement. If you took the set of all polynomials, then you have to take as a basis every conceivable positive integer power of x, right? And so that would be a basis, but there are infinitely many of those. And so P is an infinite dimensional space. If we look at the set of all n by m matrices, the canonical basis there would be, so I'll write it like this. You take a matrix where the only non-zero element occurs at the I and j of k entry. Oops, yeah, the only non-zero. All right, so that's a 1. Everywhere else you got zeros. And you do that for all I and j. I runs from 1 to n, and j runs from 1 to m. Right, and so you look at, if you form all those matrices where you just have 1 on an entry and everyone else 0, well, there are n rows and m columns. You would need n times m of those matrices. And so that's a basis, and the number of vectors in there is n times m. And so notice that if you multiply those two, the number of rows and columns, you get the dimension. All right, so this is the dimension of that space. C of R. So here we don't know what a basis for C of R is, but we do know that it contains P, right? So P, the set of all polynomials, are certainly continuous. This is a subspace of C of R. And what we know is that if that's true, then the dimension of P is less than or equal to the dimension of C of R. That was by this property up here, right? If V is a subspace of V2, then the dimensions of the one inside is smaller than or equal to the dimension of the other guy. And so we know the dimension of P is less than or equal to the dimension of C of R, but we already know dimension of P is infinity. And so this guy has to be infinite as well. All right. And then for this guy, I'll leave you go back to section 7.2, the last example we talked about. Remember there we formed a basis using all of the sequences where you had initial segments of 1s and then everyone else thereafter was a 0. There were infinitely many of those vectors that were needed, but they formed a basis for R infinity. And so the dimension here is infinity because of that, right? So I'll say C 7.2 last example in the class discussion problems. Not the class discussion problem, sorry, in the lecture for 7.2. All right, let's look at these. So now I give you a collection of vectors each time, be it functions. I call them vectors, but to me they're vectors. I don't care what they look like. They're just vectors in a vector space. But we want to determine if each set is a basis using what we know about the structure of the space and what bases have to be and what dimensions are. So notice here that this guy has a dimension of 5, right? We know that the dimension of Pn is n plus 1, so that guy has a dimension of 5. But you have 1, 2, 3, 4, 5, 6 elements in here. S has 6 elements. And so if that's true, since those are in P sub 4 rather, these can't be linearly independent, right? So since this is strictly larger than that, the members, the functions, FCNS's functions, must be linearly dependent. Hence, S is not a basis for P4. And moreover, there's one more vector. So remember, the basis gives you the dimension. And so any basis for P4 would have to have exactly 5 vectors in it. This one has 6. So you can deduce, I'm actually going one step further and making a claim about independence. But really, all you needed to know was that there are more elements than dimension. And so it can't be a basis. This way, this one suffers the opposite problem. The dimension of this guy is 2 times 2, which is 4. But there are only 3 matrices in that set. You don't have enough to generate all of them, right? And so since S has fewer elements than the dimension of that space, it can't be a basis. Even if they're linearly independent, it doesn't matter. There's not enough of them to generate every possible matrix that's 2 by 2. Okay. And then note here, have mercy, we give you all sorts of functions. We give you some polynomials, some trig functions, some exponential, some radicals, an inverse trig, and a rational one, right? That ought to be enough to generate all continuous functions, right? Nope, doesn't work. And the reason for that is, again, the dimension of C of R is infinity, right? We've already argued that because it contained all polynomials, and that's an infinite dimensional space. So there are only, even though there's a whole nice variety of functions here, there aren't enough of them, right? There are not infinitely many of those. There are only finitely many. And so what we would say is that since S is finite, so in other words, it contains finitely many elements, it can't be a basis for C of R, a space that has an infinite dimension. Okay. And so this is just kind of another routine sort of thing. I'm going to cross out this, right? And then we're not going to look at the example 6. So we're actually almost done. I'm going to stop after example 5a. So you want a basis for each of these subspaces of P4, right? So we're asking the same question, but now we're looking for bases for subspaces, right? So we're not looking to generate the whole space. We're looking for elements in the subspace that would be enough to generate that particular subspace. All right, so if you look at P4, so that's all of the quartic polynomials, degree 4, and you take the subspace consisting of all the polynomials with 0 constant term. So if you have a 0 constant term, in the basis, you don't need to include a constant because it's always 0, right? And so what you do need, though, are x, x squared, x to the third, and x to the fourth, right? Because any polynomial with 0 constant term could still have one of those guys. And so that would be a basis for this subspace. Notice that the dimension of the subspace, so the dimension of the subspace, we'll call this S. So the dimension of S is equal to 4, right? Which is strictly less than the dimension of P4, which we know to be 5. Which is good. I mean, you could actually have subspaces with the same dimension. You just can't have it with more dimension, right? You couldn't have this to be 6, but it could be anything from 0 to 5. And then if you took the even polynomials, in P4, well, then you can have a constant. You can have x squared and x to the fourth, right? So all three of those could actually form the parts of an even polynomial. So this would be a basis. Call this T. Oops. Right, so this is a basis for S. If we call that T, this is a basis for T. And notice again, the dimension of T is 3, which is less than the dimension of the space to which it belongs. Great. And then just along the similar lines, just so we don't always have to think in terms of polynomials and functions, you can also think in terms of sets of matrices, right? So we have the set of all 2x2 matrices, and we want a basis for the upper triangular matrices, right? So we only have 2x2. You want to form just enough matrices that when you add constant multiples of them together, you get an upper triangular matrix of any sort that you want. And so the one thing we know is that the lower left entry has to be 0 always, because if it's not, the minute you multiply by a scalar and add them up, you don't have a lower entry of 0, which would not produce an upper triangular matrix. But you can have anything in here, here, or here, it could be anybody. So why don't we just take a 1 on one of those entries and a 0 everywhere else? Right? Those are all upper triangular matrices. And if you multiply them by scalars and add them up, you still get a upper triangular matrix. And so this would be a basis. Let's call this U. So this would be a basis for U. That would generate all of those guys. And R2 cross 2, the dimension of that, if you remember, is 4. You multiply the 2's together to get 4. And so, and we know the dimension of U is 3. Right? And so, again, that's consistent with what we know. Okay, so it's kind of an anticlimactic end, right? We kind of ended with not a main theorem per se, but kind of an observation of what a basis and dimension are. But think of the culmination of all of this in chapter 7. That is kind of the climactic end of linear algebra 1, right? It's the fact that we had all these concepts that generalize to form a space where now you can, if you talk about vector spaces in general, right? Suppose we didn't even give examples now. Suppose we just talked about vector spaces and their properties. The minute you prove a theorem about a vector space or a vector subspace, it applies to all of these examples without having to look at each one separately and justify it, right? So the power of linear algebra is that the abstraction really gives you a bunch of power to say something about a whole slew of spaces that have the same structure, right? And so that's where linear algebra 2 would pick up if there was such a thing, is that we would actually talk about general properties of vector spaces and start proving theorems about them. And then we would recover as examples these very particular ones. But be that as it may, we're not doing that. Obviously, this is the end. So I hope you enjoyed the course as much as you can. I know it's, a thorn in the side of people often, but hopefully we made it palatable enough and encourage you to study it going forward into other classes and even deeper into the subject. All right, it's been a pleasure, and I'll see you later. Bye.